Dear students, now we are going to solve an important problem in divergence theorem with proof. State and verify the divergence theorem for the vector A is equal to 4x I vector minus 2y square j vector plus z square k vector taken over the cube bounded by x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1 and z is equal to 0, z is equal to 1. In the solution part, first we have to write the statement of this divergence theorem. As we know that the divergence theorem relates the volume integral and surface integral. That is, the volume integral of the divergence of a vector field over a volume is equal to the surface integral of the normal component of this vector over the surface bounding that volume. So that's what given here. Volume integral of the divergence of this vector field is equal to the surface integral of the normal component of this vector. So this can also be written as A dot n ds. Here n represents the normal component. Okay. So next we are going to verify the divergence theorem for the given vector A is equal to 4x I vector minus 2y square j vector plus z square k vector. Okay. First, we are going to take the left hand side of this divergence theorem, that is the volume integral of the divergence of the given vector. So here, divergence of a given vector del dot A is equal to, del can be represented as dou by dou x I vector plus dou by dou y j vector plus dou by dou z k vector dot that A vector value. So here we are going to perform the dot product. So we can get dou by dou x of 4x, that is here I dot I is equal to 1, j dot j is equal to 1, k dot k is equal to 1. The cross multiplication, that is I dot j is equal to 0, I dot k is equal to 0. Likewise, okay. So we can get that answer as dou by dou x of 4x plus dou by dou y of minus 2y squared plus dou by dou z of z squared. Okay, then we have to differentiate with respect to x, y and z. We can get 4 minus differentiation of minus 2y squared is minus 4y plus dou by dou z of z squared is equal to 2z. Okay. So this is the answer for the divergence of the A vector. Next we are going to take the volume integral for this divergence. So here we can write triple integration with the limits 0 to 1. Then we can write del dot A value here and dx, dy, dz. Okay. We are going to integrate with respect to x, y and z. First we are going to integrate with respect to z. So this term becomes 4z minus 4yz plus 2z squared by 2. Its limits from 0 to 1. 2 is getting divided each other. Then we have to substitute the limits here. So z becomes 1. So 4 into 1 minus 4y into 1 plus 1 squared. So 1 squared means 1 here. So we can add these two values. We can get 5 minus 4y dx dy. Then we have to integrate with respect to y. This term becomes integration from 0 to 1, 5y minus 4y squared by 2, limits from 0 to 1 dx. Okay. So then substitute the limits here. 5 minus 2, that is equal to 3. And then we have to integrate with respect to x, that is 3x with the limits 0 to 1, that is equal to 3. So we have obtained the left hand side of the divergence theorem as volume integration of the divergence of the vector field is equal to 3. Consider that as the first equation. So next we are going to consider the right hand side. So here it is surface integral of the normal component of that vector field. That can be written like this. Okay, so surface integration of A dot I vector. So that is normal component for this y and z. So we can write like this: A dot I vector dy dz. I represents x direction. Okay. So next integration in the opposite direction, that is minus I. Likewise we can take the j vector value here, dx and dz. These two are normal to this one. Okay. So we have to take the j vector with respect to dx dz. Similarly minus j, then k vector and then minus k vector. Do you all understand? So here we are going to consider the normal component of the vector field. So x is normal to this dy dz. Likewise here j represents y direction. So this is normal to x and z. Finally k is normal to x and y direction. Okay. Consider this as the second equation. So next we are going to find out the values for each surface integration separately and then substitute those values in the second equations to get the overall surface integration. First we are going to find the value of a dot I vector dy dx. So here surface integral over 0 to 1 of this a vector 4x I vector minus 2y square j vector plus z square k vector dot I vector dy dz. Okay, so next we have to take the dot product. For the dot product we can have the value for this I vector, that is 4x, because I dot I value is equal to 1. J dot I is 0, K dot I is 0. So we can get integration, that is surface integration over 4x with respect to dy and dz. So first we are going to integrate with respect to z. So here it is 4xz, the limits from 0 to 1, and then we have to get that answer as 4x, correct? Z is equal to 1 means here 4x. Then we have to integrate with respect to y, that is 4xy. With the limits from 0 to 1 we can get 4x. Okay, this is the answer for that surface integration. Since x is equal to 1 in I vector, that is given in the problem, right? It is bounded by cube, that value is equal to 1 in I vector. Then this term becomes 4 into 1 is equal to 4. So surface integral of a dot I vector dy dz is equal to 4. And then in the opposite direction, okay, so in that direction its value is 0. So we can mention that value as 0. Next consider the j normal component. So here it is surface integral of a dot j vector dx dz is equal to double integral of 4xi minus 2y square j plus z square k vector dot j vector dx dz. So here we are having the value only for this j vector because j dot j is equal to 1. So that is minus 2y square. Then we are going to integrate with respect to z. This becomes minus 2y squared z with the limit 0 to 1. Okay, substitute the limits here. So z becomes 1. So here we can get integration over 0 to 1 minus 2y squared dx. Then integrate with respect to x. We can get minus 2y squared x from 0 to 1. Substitute this value. We can get minus 2y squared. Okay. As we know that the value of y is equal to 1 in the j direction, we can substitute that value here. So this integration becomes minus 2. That is surface integration of a dot j vector dx dz is equal to minus 2. In the opposite side, its value is 0. So we can say a dot minus j vector dx dz is equal to 0. Similarly, we can obtain the value for this a dot k vector dx dy. Okay, so here the same way we can substitute the value of this a vector here and take the dot product for this k vector. We can get z squared. Then integrate with respect to y, that is z squared y with the limit 0 to 1. Substitute that limit here. So this integration becomes integration of z squared dx, that is equal to z squared into x from 0 to 1. And then substitute that limits, we can get the value as z squared. As we know that z value is 1 in the k direction, so we can substitute that value here. So 1 squared is 1. In the opposite side, its value is 0. So we have found all the surface integral terms. Then substitute all those values in the second equation. Then we can get surface integration of a dot ds is equal to 4 plus 0 minus 2 plus 0 plus 1 plus 0. That is equal to 3. Consider that equation as third equation. Compare the first and third equation. We can get that right hand side is equal to left hand side is equal to 3. Hence the divergence theorem is verified.